Today, we will be helping Dora to go to the library by learning Chapter 9, Comparing Two Means.
Let's get started on our adventure to the library! Vamonos! Let's go to the library!
Hi, I'm Meridel C. Kileste and I welcome you to my PowerPoint presentation. Sometimes in science we want to do the same thing, to compare two things to see if there is evidence that one is different to the other. In this presentation is all about the process of comparing two means using t-test. Now, what is comparing two means? It means gathering of information of two populations in order to compare them. For example, if we take two groups of people and randomly assign one group a program of dieting pills and the other group a program of sugar pills, which they think will help them lose weight, then if the people who take the dieting pills lose more weighting than those on the sugar pills, we can infer that the diet pills cause the weight loss. Now let's proceed to the two different ways of collecting data. You see there that there is between group or independent design. It means that we can either expose different people to different experimental manipulations. Next one is the repeated measures design, which means taking a single group of people and expose them to different experimental manipulations of different points in time. Now let's proceed to a problem with error bars of graphs repeated measures design. Now prepare your Spider BG subfile and your Spider RM subfile. So now we are looking at a problem that occurs when we graph repeated measure error bars. Now we're going to look at this example of the Spider RM BG file. RM BG file subfile. Okay, you have it there. So in this example relates to whether an arachnophobia or fear of spider is specific to real spiders or whether pictures of spiders can evoke similar levels of anxiety. You have there 24 arachnophobes were used in doll. 12 were asked to play with a big hairy tarantula spider with big fangs and evil look in its 8 eyes. Their subsequent anxiety was measured. The remaining 12 were shown only pictures of the same big hairy tarantula again. Their anxiety was also measured. Remember that each row in the data editor represents different participants' data. Therefore, you need a column representing the group to which they belong and a second column representing their anxiety. Remember that code of 0 represents the group that were shown with a picture and the code 1 that represents the group that saw the real spider. Now let's open our Spider RM subfile. Okay, so you have there your RM subfile. So now let's imagine that we're collecting these data using the same participants, that is, all participants had their anxiety rated after seeing the real spider but also after seeing the picture. Okay, you have there the data would now be arranged differently in your SPSS file. Instead of having a coding variable and a single column with anxiety scores in, we would arrange the data in two columns, one representing the picture condition and one representing the real condition. Okay, note that anxiety scores are identical to the between group data. It's just that we're pretending that they came from the same people rather than the different people. Okay, now let's go back to our error bars. Okay. These error bars comes from our Spider RM subfile. Now these error bar graphs from two different designs. Remember that the data are exactly the same. All that has changed is whether the design used the same participants repeated measures or different or independent Now, we discovered in that repeated measures designs, we eliminate some extraneous variables such as age, IQ, and so on, and so can give us more sensitivity in data. Therefore, we would expect our graphs to be different. The repeated measures graph should reflect the increased sensitivity in the design. Looking at the two error bar graphs, you can spot this difference between the graphs. Hopefully your answer was no, because, of course, the graphs are identical. This similarity reflects the fact that when you create an error bar graph of repeated measures data, SPSS treats the data as though different groups of participants were used. In other words, the error bars do not reflect the true error around the means of repeated measures design. Fortunately, we can correct this problem manually, and that's we will discover now. Now, let's go to our step-by-step procedure in how we're going to look at the difference. So you have here next, which is the step 1. So step 1 is you're going to calculate the mean for each participant. Okay, so we need to use the compute command by first go to transform, then compute variable, and then in the target variable you enter the mean, name mean into the box called target variable, and then in the list labeled function group select statistical, and then in the list labeled functions and special variable select mean. Transfer this command area by clicking the arrow up. When the command is transferred, it appears in the command area as mean with all caps. The question marks should be replaced with variable names which can be typed manually or transferred from the variables list. So replace the first question mark with a variable picture and the second one with a variable real. The completed dialog box should look like as what you have seen. Now click on OK to create this variable, which will appear as a new column in the data editor. Okay, you can now see that there is another additional column in your data view, which is the mean column. Now let's proceed to step 2, which is you're going to calculate the grand mean. So what is grand mean? It is the mean of all scores regardless of which condition the score comes from. And so for the current data, this value would mean of all 24 scores. One way to calculate this is by hand, so simple as adding up all scores and divided by 24. However, easier way is to use the means that we have just calculated. The means we have just calculated represents the average score for each participant. So if we take the average of those mean scores, we will have the mean of all the participants, or the grand mean. Cool. There were a lot of means in that one sentence. Okay, to do this, we can use a useful little gadget called the descriptives command. You can also use the explore or frequencies functions that came across. So now access the descriptives command by selecting analyze, then descriptive statistics, then descriptives. Okay, you see there a descriptives dialog box, and then the descriptives command used to get basic descriptive statistics for variables, and by clicking options, a second dialog box is activated. Then select the variable mean, then the list, and transfer it to the box labeled variables by clicking that one by clicking the arrow. Then use the option dialog box to specify only the mean You can leave the default settings as they are, but it is only the mean in which you are interested. Then continue. If you run this analysis, the output should provide you with some self-explanatory descriptive statistics for each of the three variables, assuming you selected all three. Then you should see that that when we get the mean of the picture condition and the mean of the real spider condition, but it's actually the final variable we're interested in, the mean of the variable and the spider condition. So the mean of this variable is the grand mean, and you can see from the summary table that its true value is 43.5. We will use this grand mean in the following calculations. Now let's proceed to our step 3, okay, which is calculating the adjustment factor. If you look at the variable mean, you should notice that the values for each participant are different, which tells us that some people had greater anxiety than others did across the conditions. The fact that participants' mean anxiety scores differ represents individual differences between different people. So it represents the fact that some of the participants are generally more scared of spiders than others. These differences in natural anxieties of spiders contaminate the error of bar graphs, which is why we don't adjust the values we plot. We will get the same bar graph as an independent design that had been used. Now, we can use the compute function to do this calculation for us. Now we can activate the compute dialog box, give the target variable name suggested as adjustment, and use the command 43.5-mean. This command will take the grand mean of 43.5 and subtract from each participant's average level anxiety. Then press OK. Now you can see that there is another column, which is the adjustment. Now this process creates new data in editor, which is adjustment, and this scores the column adjustment represents the difference between each participant's mean anxiety and the mean anxiety level across all participants. You'll notice that some of the values are positive, and these participants are ones that were less anxious than average. Other participants were more anxious than average, and they have negative adjustment scores. We can now use these adjustment values to eliminate the between subject differences in anxiety. Now let's proceed to step 4. Create adjusted values for each variable. So far we have calculated the difference between each participant's mean score and the mean score of all the participants, or the grand mean. This difference can be used to adjust the existing scores for each participants. First, we use to adjust the scores in the picture condition. Once again, we can use the compute command to make the adjustments. Activate the compute dialog box the same way as before, then title our new variable picture underscore adjusted. Then you can click on type and label and give this variable a label such as picture condition colon adjusted values. Then continue. All we are going to do is to add each participant score in the picture condition to either adjustment value. Select the variable picture and transfer it to the command area by clicking the arrow. Then click on the plus button and then select the variable adjustment and transfer it to the command area by clicking the arrow again. Completed the dialog box is shown, and now do the same thing, then click OK. Then do this the same thing for the variable real. Now we're going to first type real underscore adjusted that contains the values of real added to the value in the adjustment column. Then also adjust the label to real condition adjusted values. Then continue. Then change it to real, then arrow, then press OK. Now you can see that there is another added column for picture adjusted and real adjusted. Now variables real adjusted and picture adjusted represents the anxiety experience in each condition adjusted so as to eliminate any between subject differences. If you don't believe, then use the compute command to create this variable mean2 in this average of real adjusted or picture adjusted. Should you find the value in this column is the same for every participant, thus proving that the between subject variability means is gone. The value will be 43.5. Now let's proceed to this slide. So what do you see in these two graphs? So comparing these two graphs, the first thing you notice is that the means in the two conditions have not changed. However, the error bars have changed, they have got smaller. Also, whereas the error bar graphs overlap, in this new graph they do not. We have also discovered when error bars do not overlap, we can be fairly confident that our samples have not come from same population, and so our experimental manipulation has been successful. Therefore, we plot the proper error bars for the repeated measures data. It shows the extra sensitivity that this design has. The differences between conditions appear to be significant, whereas when different participants are used, there does not appear to be significant difference. Remember that the means in both situations are identical, but the sampling error is smaller in the repeated measures design. So that would be all. Thank you. So looking at differences, let's have a quick recap. Step 1, you have their calculated mean for each participant. Step 2, calculate the grand mean. Step 3, we have their calculate the adjustment factor 2. And lastly, create adjusted values for each variable. So that's it. Thanks.
Look! It's the Fiesta Trio!
Hello, my topic is all about the basics of t-test. Now, let me share with you why do we need to know about t-test. By using t-test, we would be able to understand better the results of our study and why are there differences in the results. Now, let's define t-test. So basically, a t-test is a statistical test that is used to find out if two sets of data are significantly different from each other. It basically compares two sets of data and their means. Now let's take a look in our example for today. So we will be comparing two sets of data. In our example, we will be comparing the anxiety level of the audience watching the movies Scream Part 1 and Scream Part 2. Now, we will be doing this by measuring the heart rate of the same group of people while they are watching the two movies, which is the Scream Part 1 and Scream Part 2. By simply performing a t-test, we would be able to identify if there is a significant difference in the results between the two sets of the data we have. Now, the t-test assumes the data follows a normal distribution. As we can see, there is a bell curve formed here, and that variances of the two groups of data are to be equal. Now, the t-test also uses what we call a null and alternative hypothesis, and I believe null and alternative hypothesis has already been discussed before in the previous chapter, so this will just serve as a sort of review. So when we say null hypothesis, it states that there is no difference between the groups. So we have here an example: the effect of biofertilizer X on plant growth. So to state the null hypothesis, we can say it or state it as application of biofertilizer X do not increase the plant growth. So meaning to say, if we put the biofertilizer X, it will not have an effect on the growth of the plant. If we say it's an alternative hypothesis, it means that there is a difference between the two groups. So in the same example earlier, so if we will be stating the alternative hypothesis, we can say it as, or state it as, application of biofertilizer X increase plant growth. So meaning to say, if we apply biofertilizer X, it will significantly increase the growth of the plant. Now let's move on to what we call a p-value. Now a p-value, it is a value resulting from a t-test, and it will basically tell us how likely the difference between the two groups we are actually comparing have happened by accident. So if we take a look here at the table, this is actually an example of a t-test result on SPSS. So in this table, the p-value is located here in this column with the symbol SIG, which probably stands for significant or significance. Now, if the p-value is less than 0.05, then statistically there is a significant difference between the two groups that we are actually comparing. Let's try to summarize about the p-values. Now, if we see that the p-value is actually less than 0.05, then that means that the null hypothesis is to be rejected. And then if the p-value is equal to 0.05, it would also mean that the null hypothesis will also be rejected. But in the case that we see that the p-value is greater than 0.05, then meaning to say the null hypothesis will not be rejected, or meaning to say the null hypothesis is to be retained. So basically, by knowing or performing t-test, we would be able to identify what to do with our null hypothesis and alternative hypothesis. Now, here on chapter 9, we basically focus on testing the difference between two population means, or comparing the means of two sets of data. Because sometimes researchers deal with describing and testing hypotheses that involve not just a single group of data, but instead they study two groups of data and then they try to compare them in order to see if there is a significant difference between them. Now, in performing tests or comparing two means, we sometimes follow two different versions of the t-statistics. And the first one is what we call an independent t-test. Now, this t-test procedure is used to compare the means of two normal groups which are independent of one another. So this means that the groups are not related in any way. So from the name itself, independent, meaning to say independent, it can stand alone, it is not related with one another. Okay? Now, the second one is what we call a dependent means t-test. This t-test procedure is used to compare the means of two groups which may be related in some ways. For example, we gave a pre-test and post-test to our students, and we wanted to compare the results of the pre-test and the post-test. In that case, we will be using a t-test to compare the pre-test and post-test scores of our students. Now, since I have already mentioned the two types of t-test that we can use, my group mates will also be discussing in details the difference about independent t-test and the dependent means t-test. So thank you for listening and watching.
Adios, Señor Troll!
Hello everyone, this is Nina and I'll be talking about the dependent t-test and to make our lives easier, how to run it using the SPSS software. So what is the dependent t-test? It is simply the t-test used when there are two conditions and the same participants took part in both conditions. This is sometimes called the matched paired or paired samples t-test. Let's talk about one comprehensive example of this. In an experiment, there were 12 participants. All of them were arachnophobics, or they were afraid of spiders. On one occasion, they were exposed to a picture of a spider, and on a separate occasion, they were exposed to a real-life spider. Here, their anxiety levels were measured after each occasion, and we wanted to see the difference in their anxiety levels between the two conditions or the two occasions. The dependent t-test would help us determine whether the difference observed was a chance result or not a chance result. So if it was a chance result, then it must have happened by chance and it is not caused by the experimental manipulation. Now, if it wasn't a chance result, then it must have been really caused by the experimental manipulation. So, how do we run the dependent t-test using the SPSS software? Well, we'll just have to follow these steps. Number one would be to prepare the data. And here we have the data on the arachnophobics experiment downloaded from the SPSS datasets by Dr. Robert J. Padgett. So what should we do with this data? That leads us to the second step, which is to select Analyze, and then Compare Means, and then Paired Samples t-test. Well, I'll show you a picture here. So on the top part of your software, you'll see Analyze. You'll just have to click on that, then Compare Means, and then the Paired Samples t-test. Then it would show you a dialog box like this one. Now what should we do with this dialog box? That brings us to the third step, which is to select a pair. Now to select a pair, you'll have to click on the first variable that you want, in this case the picture. Then hold the control key on the keyboard and select the second, in this case real. And both of them would be highlighted like this. So after that, you'll have to click on the arrow in the middle to transfer the variables to the box labeled paired variables. So as you can see here, we have an arrow. So you'll just click on that and these variables would be transferred to the paired variables box. So what would be the next step? Okay, click options and choose a confidence interval percentage. So you click options and it will show you a dialog box like this one. In this case, let's just choose the 95% confidence interval percentage. You'll click continue, and then this dialog box would disappear. And to run the analysis, just click on OK and wait for the results. SPSS would generously give us this output, which shows us all the values needed to analyze the data that we have gathered. So in the first table here, you can see the mean, the number of participants, the standard deviation, and the standard error mean of each condition, picture and real. In the second table, you can see that the Pearson's correlation is being shown. We can see that the correlation coefficient 0.545 is fairly large, but the p-value is 0.067, which is greater than 0.05. So that means that the two conditions here are not significantly correlated. But you don't really have to think about that very much, because our focus here is the dependent t-test. So let's move on to the third table, which is considered to be the most important of all the tables, since the values we can see in this table are going to help us reach our objective, and that is to know whether the difference between the mean scores of the two conditions was large enough to not be a chance result. So first, the table tells us the mean difference between scores. Here, that's -7,000. So that's 40 minus 47 equals -7. The standard deviation is 9.807, and more importantly, this table shows us the standard error mean, which is 2.831. So we have here the mean and the standard error mean, which are very important to calculate for the t. So the SPSS divided the mean, which is -7, by the standard error mean, which is 2.831, to get -2.471. So that's our t value. We also have our degrees of freedom here, df. That's labeled df, which is 11, because that's 12, the number of participants, minus 1, 11. And on the last column, we can see the probability value, or the p-value, which is 0.031. That's labeled sig two-tailed. What does it mean? That's the probability or the likelihood that a t-value that big can occur if the null hypothesis were true, or if the experimental manipulation was unsuccessful. Now, everything we've talked about here leads us to three very important points. That's number one. Number one is that the probability obtained is only 0.031. Therefore, there is only a 3.1% chance that the value of t this big could happen if the null hypothesis were true, or that the experimental manipulation wasn't successful. Now, that's a pretty small probability we have there. Number two, we generally accept a p-value which is less than 0.05 as statistically meaningful. Now, 0.031 is less than 0.05, so that means that our t is significant. The third point is that the t-value is negative. As you can see here, that's negative. That means that the first condition had a smaller mean than the second condition. Therefore, the real spider caused a greater anxiety than the picture. Therefore, we can conclude that the exposure to a real spider caused significantly more reported anxiety in arachnophobics than exposure to a picture. Since the t-value was significant, we can confidently say that the result wasn't just a chance result. It was really caused by the experimental manipulation. Our t-value is, yes, significant, but another question that we have to take into consideration is that, is it large enough? So that's why we have to talk about the effect size. Now, how do we calculate for the effect size? We'll just have to do it by converting t to r, or the effect size. So we just have here an equation that we can use. R equals the square root of t squared divided by t squared plus the degrees of freedom. So we already know the values of t and the degrees of freedom, so we'll just have to substitute those values here. So that's negative 2.473 squared divided by negative 2.473 squared plus 11. Let's do the math, and eventually we'll come up with the result, which is 0.60. Now let's analyze this result. Okay, so this is obviously greater than 0.50, which is the threshold for a large effect. So we can confidently say that the effect is not only statistically significant but also significantly large, and so represents a substantive finding. Finally, we'll have to talk about how to report the dependent t-test. So we could write on our paper, on the average, participants experience significantly greater anxiety to real spiders. Open parenthesis, M equals 47.00. M here means mean. Comma, SE, standard error, equals 3.18, close parenthesis. Then to pictures of spiders. Open parenthesis, M equals 40.00, comma, SE equals 2.68, close parenthesis, comma, T, open parenthesis, 11, close parenthesis. So 11 here is the degrees of freedom, equals negative 2.47, comma, P is less than 0.05, comma, and R equals 0.60, period. So you can just read it as, on the average, participants experience significantly greater anxiety to real spiders than to pictures of the spiders. But on your paper, it would be very important to include the means of the two conditions, their standard errors, and of course your t-value, and of course the p-value. Now the R, or the effect size, is not really that common, but it would really help if you could also include that. That concludes this presentation. However, I would like to note that all the things that you can see in this video can be found in Andy Field's book, Discovering Statistics Using SPSS 3rd edition. Thank you so much for watching the video. I hope that you have learned something. Thank you. Bye.
Thank you.
Hello guys, this is Jamel Jackson and I'm here to talk about the independent t-test. Since we are done talking about the dependent t-test, this time we will venture on its counterpart, the independent t-test. Now, what is the independent t-test? The independent t-test is used in situations in which there are two experimental conditions and different participants have been used in each condition. So when we go back to the dependent t-test, it's looking on the differences between pair of scores from the same participants. But if we talk about independent t-test, it's looking on the differences between different participants. This means that this test compares the differences of the overall means of two different samples. Now, how do we compute on this test? We have here the formula in conducting the independent t-test. T is equals the sample mean of group 1 minus sample mean of group 2 over the square root of pooled variance over sample size of group 1 plus pooled variance over the sample size of group 2. The derivation of this formula is mind-blowing, so we will go directly on finding the results, not manually, but by using our best friend, the SPSS program. This is really a great tool in calculating since with just one click, all of the needed informations will show, but of course, the needed informations will show if we know how to manipulate it. This time, let's go to the program, and for our data, we will use again the data spider BG. This data contains the anxiety level of people who saw the spider through a picture and the people who saw the spider in reality. We want to find out which group experienced greater anxiety, so we will be using the independent t-test. We have here our data, the group column and anxiety column. Before we will do the test, check first the value used on the group column by clicking the value labels on top. After clicking, you can see that the numbers used are 0 and 1. Take note for these numbers since we will use these numbers in the test. After knowing the value, click Analyze, click Compare Means, and select Independent Samples t-test. As you can see, there are two boxes we need to fill in, the box for test variable and grouping variables. For the test variable, you have to put the anxiety data, which is a scale variable. Always put in your mind that the data you have to put in this box is a scale variable. Then, put the group data in the grouping variable. This is to let the program identify the two groups in your data. Click the Define Groups and write the value labels on the group which we checked a while ago, number 0 for group 1 and number 1 for group 2. No need to change the settings in the options. Now that everything is set, let's run the test by clicking the OK button. As you can see, there are two tables presented on the test, the group statistics table and the result table from the independent t-test. These two tables are very important in interpreting the data. Let's analyze and interpret the tables one by one. On our table 1, it shows the summary statistics for the two experimental conditions. From this table, we can see that both groups had 12 participants from the column labeled N. The group who saw the picture of a spider had a mean anxiety of 40 with a standard deviation of 9.29. It shows also the standard error of 2.68. In addition to this, data of the participants who were shown a real spider were presented in the table. It shows a mean average of 47 with a standard deviation of 11.03 and standard error mean of 3.18. These data are very useful when we will report our findings, so we cannot just ignore this table. Let's go to our second table, the main test statistics. You have noticed that there are two rows on the first column of the table. We have the equal variances assumed and the equal variances not assumed. This is due to the column labeled Levene's test for equality of variance. If the significant value is less than 0.05, then the assumption of homogeneity of variance has been broken, and therefore, we should look at the row labeled equal variances not assumed. However, if the significant value of Levene's test is bigger than 0.05, then we should look at the row labeled equal variances assumed. In our case, since the significant value is greater than 0.05, we should look at the row of equal variances assumed. Now that we already know which row to look, let's go to the other column, which is the t-test equality of means. It shows various data such as the t-statistic, degree of freedom, significant value two-tailed, mean difference, standard error difference, and 95% confidence interval of the difference. But to make it short, we just have to look for the significant value to tail column. If the result in this column is less than 0.05, then the means of the two groups are significantly different. But if it's more than 0.05, it means they are not significantly different. In our case, since the value is 0.107, it means that there is no significant difference on the anxiety level between the two groups. But aside from this information, we also need to know if the effect is substantive. Therefore, we need to calculate the effect size to report more details about the study. Effect size is a statistical concept that measures the strength of the relationship between two variables on a numeric scale. So, we have to use the formula R is equal square root of t squared over t squared plus df or degree of freedom. If the result is 0.10, it shows small effect, which means the effect explains 1% of the total variance. If it's 0.30, it shows medium effect, which means the effect accounts for 9% of the total variance. And lastly, if it's 0.50, it shows large effect, which means the effect accounts for 25% of the total variance. In our case, we compute the effect size and we got a result of 0.34, which represents a medium effect. Therefore, even though the effect was non-significant, it still represented a fairly substantial effect. So, to report our results in our study, we can use this format taught in the book. On average, participants experience greater anxiety to real spiders than to pictures of spiders. This difference was not significant. However, it did represent a medium-sized effect. As you can see, data are also presented in the parentheses. We have the M as mean of each group, SE for standard error of mean, T for T statistic with 22, which is the result for the degree of freedom equals to the T statistic in the table. We also included the rule wherein our results or the p-value is greater than 0.05. In our case, we have 0.107 as our p-value. At the last part, we also stated the effect size result, which is R equals 0.34. In this manner, you can report in detailed and organized. So to summarize everything, we have some tips to help you. Thank you for listening, everyone. I hope at the end of this talk, you can be able to calculate, analyze, and interpret data using independent t-tests.
Now we can go down the rock and to the library.
Hello, my topic is about t-test as a general linear model. If you can recall our topic about t-test is actually a statistical test wherein we try to compare the means of two different sets of data. But this time, we will be using the t-test as a general linear model. Now, by using the linear model, this will allow us to actually predict the value of the dependent variable given some new values of the independent variables. And having said that, if we want to predict the outcome, so what we will be doing is we will be using this general equation, which is outcome sub I is equal to model plus error sub I. But since, as I've mentioned earlier, we will be using a linear model, we will be using this equation instead. So we will be using A sub I is equal to B sub 0 plus B sub 1, G sub I plus error sub I. Now, A sub I, it is for the dependent variable or the outcome. So for the b sub 0, this will represent the intercept. The b sub 1 will represent the weighting of the predictor, while the g sub I will be the independent variable or the predictor. Now the uppercase letter A will represent anxiety, while the uppercase G will represent the group. Now, we will be using this linear model equation in our next activity. Now, in our next activity, we will be using the spider.rm.sav file. So let's try to open the spider.rm.sav file. Now that we have opened the spider.rm.sav file, this file basically shows us the data between the level of anxiety measured for the different participants when they were shown real spider, this column, and their anxiety level whenever they were shown the picture of a spider. Now let's try to analyze the data and get the mean of the picture and the mean of when they were shown the real spider. So let's click on Analyze, click on Descriptive Statistics, and click on Descriptives. So for the variable column, we need to transfer the picture of the spider, real spider, and the mean. And then let's click on Options, click on Mean. Let's include also standard deviation, minimum, and maximum. And let's click on Continue. Let's click on OK so that we can view the table. Now that we have the table here for our descriptive statistics, we will be transferring or copying this table to our file here. Okay. For our file, so the descriptive statistics, let's take a look here, focusing on the mean. So for the picture of the spider, the mean is 40, while the mean for the real spider is 47. So we can see here that we have a total of 12 participants. Now, using those data, let's try to use that in our general linear model equation. So we have here the general linear model equation. This time what we will be doing is that we will be using what we call a dummy variable. Now, in a dummy variable, what we do is we basically give codes, okay, or coding or values for the groups. This one. So for example, in our first example here, using the general linear equation model, so what we will be doing is we will be replacing the outcome, okay, or the dependent variable. We will be using the anxiety that the people feel when they were shown the picture of the spider. So here, mean for the picture is equal to b sub 0, or the intercept, plus the b sub 1, or the weighting of our predictor, and then we will be using the value, remember, dummy variable for the group sub I, we will be using the value of 0 this time. So we have 0 over here. So b sub 1 times 0 is 0. So what will remain in our equation will be the mean of the picture and the b sub O, or b sub 0. Now, going back, looking here, okay, so the b sub 0 is also equal to the mean of the picture. Now, going back to our table earlier, so we can see that the mean for the picture of the spider is, we have here 40. Therefore, replacing this one with its value of 40, we can say that b sub 0, or the intercept, is also equivalent to 40. Therefore,
the b sub 0 or the intercept is also equal to the mean of the picture of the spider. Now, this time let's try the other outcome or the other dependent variable, which is the real spider this time. And using dummy variable, we will be replacing the code for the group or the value of the group. Instead of 0 earlier, this time we will be replacing it with a value of 1. So let's continue. The mean of the real spider is equal to b sub 0 plus b sub 1, multiplying it with the value of 1. So b sub 1 times 1 will give us b sub 1. And then we have the mean of the real spider is also equal to the mean of the picture. Where did we get this one? The mean of the picture here, because remember earlier we used to say that the b sub o or our intercept is also equal to our mean of the picture of the spider. So we will be replacing it with this one. Now, next step is that we will be transposing the mean of the picture to the other side of the equation. Therefore, what we will be having will be b sub 1 is equal to the mean of the real spider minus the mean of the picture. So going back to the table, replacing it with its value, so the mean for the real spider we have 47, while the mean of the picture is 40. So 47 minus 40 will give us 7. So meaning to say our b sub 1 is equal to 7, or the weighting of our predictor is equal to 7. Now, this time we will be using another set of file, which is the spiderbg.sav, and we will be running a regression test on this one. So let's open the spiderbg file here. So spiderbg file, so we will be running a regression test. So we can do that by clicking on analyze, click on regression, then click on linear. Now for the independent variable, let's insert the spider or picture. And then for our dependent variable, let's use the anxiety. Now let's click on statistics, click on model fit, and click on descriptives, click on continue, and click on OK. Let's check our table. Now that we have here the regression, the result of the regression test, we have there the descriptive statistics, but let's focus here on this part for the coefficients. Okay, so let's copy this one in our slide here. So let's take a look at the table which shows the regression coefficients for the real spider and the picture of the spider. We can also see here the standard error. We can see here the standardized coefficients. We can also see here the t-score and also the p-value. Now, let's focus on the p-value of the real spider and the picture of the spider. So here we can say that the p-value is at 0.107. So having a p-value of 0.107, which is basically greater than 0.05, so that would mean that there is no significant difference between the means of the two samples. Now, basically by doing and performing a t-test, we would be able to demonstrate or see the difference between the means, and representing it in terms of linear models, This will be useful whenever we talk about or we discuss further the topic about the general linear model. So that will be all for my topic for today. Thank you for listening and watching.
Look! It's the Fiesta Trio! The library bell! That means the library's going to close soon! Come on, let's go return my books! Look! It's the Fiesta Trio! They have a sticker for your sticker box! Yes! Wow! We all have books! Thanks, Val!
You're welcome, Dora.
We couldn't have done it without you! We took back my library books! And we all got new ones! Great books! We